share my screen, and welcome everybody to today's Tech Talk, CIMAC Tech Talk, about engine components and basic research. Pleasure to have you here. It's now 2 p.m. in Germany, at least 2 p.m. afternoon, and we'd like to start with our today's Tech Talk. Unfortunately, two of our speakers which were planned for today had to cancel due to illness, and just the latest information came in from Oliver Lehmann that he won't be able to join today. So I'd like to give over the word to Gerhard Picker from LEC, who is our moderator today, and he will introduce our speakers, and I'm very much looking forward to today's Tech Talk, and welcome, and thank you for joining. And Mr. Picker, the word is yours. Thank you.
Okay, thank you, Mr. Erdmann. I would also like to welcome you to this Tech Talk from my side. As you already said, my name is Gerhard Pirker from LEC, and unfortunately today we have only two presentations. And after each presentation there will be a Q&A session, and for that I would like to ask the audience to type their questions into the questioning tool so that I can read them out to the presenter during the Q&A. You can already write down your questions during the presentation so that they are available in time, and I think the questioning tools opens if you click on the question mark icon on the right side of the screen, if I remember correctly. Okay, then let's begin. Our first speaker is Mr. Melan Thompson. He is standing in for Mr. Wang from Shanghai Jiaotong University, who is unfortunately unable to attend today. And his presentation will be about an empirical model of uniflow scavenging for a long-stroke marine low-speed diesel engine. Mr. Thompson, the stage is yours.
Okay, I'll start right now. Hello, everyone. Oh, sorry. Okay. Sorry, I have to minimize. Hello, everyone. My name is Xianping from Shanghai Jiaotong University. Today, I'm going to introduce my study on the topic of empirical model of uniform scavenge ultra-long two-stroke marine diesel engines.
Sorry, Mr. Thompson, we cannot see your screen.
You cannot?
No. Or can somebody?
Well, I can see the screen.
Okay.
I see a presentation.
I have shared my screen.
Okay, sorry, then
yeah.
it's on my
You're good,
hand.
Mr. Thompson. We can see your screen.
Okay, then
Mr.
go on.
Picker,
Now I also can see it. Sorry.
Okay, perfect.
Thank you.
Okay.
Thanks.
And my introduction consists of 5 parts: introduction, and the experiment setup, numerical analysis, and model development and conclusion. Owing to the advantages of large power range, high thermal efficiency, low fuel consumption rate, and good reliability, marine low-speed engines are widely adopted to provide power to civil ships. The market for low-speed engines is vast, and improving the performance of low-speed engines through research has great economy and environmental significance. The figure on the right shows the trend of power source of marine. It shows that the number of marines powered by the low-speed engine has increased from 110% from 2000 to 2011, and nowadays over a half a marine use low-speed engine as a power source. As we all know, the two-stroke engine operation cycle consists of 4 periods, and among them, the scavenge process of the marine low-speed engine covers the entire stage from the opening of the scavenge port to the closing of the exhaust valve. During each stroke, the scavenge process not only cleans the combustion exhaust gas in the cylinder, but also provides fresh air for the combustion in the next cycle. Simultaneously, the scavenge process must provide a certain initial vortex for the intake air. In the fuel injection stage, the appropriate stress of the cylinder vortex can promote a uniform mixing of fresh air and fuel, and subsequently achieve fuel combustion of the mixture. And historically, there are 3 kinds of scavenge type: crossing scavenge, loop scavenge, and uniform scavenge. The biggest difference between the 3 types of scavenge is the arrangement of scavenge port and exhaust valve. And the figure shows on the right, shows a comparison of the scavenge efficiency for 3 types of scavenge methods. As we can see, the uniform scavenge has the highest scavenge efficiency at all delivery ratio. And besides, due to meet the requirements of ship owners for low fuel consumption and IMO's regulation of having the greenhouse gas emission of newly built ships, the ultra-long stroke of low-speed engine has become a trend. With an ultra-long stroke, the combustion speed of low-quality fuel oil is low, and an ultra-long stroke cylinder can prolong the expansion process and improve the combustion process and reduce the fuel consumption rate. The ultra-long stroke diesel engine further create fuel saving of 3.5 to 7% based on original low fuel consumption. And in summary, the developed trade of 2-stroke engine are low stroke or ultra long stroke will be future developed trends, and uniform scavenge gradually replace cross scavenge and loop scavenge. And the low speed engine will set the scavenge port angle to make the cylinder have the strong organized vortex flow and stabilize the microflow of the gas. But at the cost of experiments for low-speed 2-stroke engine is doubting, and at the developing stage, extensive wide-dimensional performance simulation are adopted to reduce the cost and accelerate the development, especially in the area of digital manufacturing. And furthermore, in the conceptual design stage of the engine, safety calculation could not even be carried out due to the lack of the specific geometry data. And owing to the decisive role in the scavenge process plays in engine performance, accurate scavenge model for modern low-speed engine must be provided. There are many 2 types of scavenge model for low-speed engine: the single-zone model and multi-zone model. There are also 3 types of single-zone model: the complex, the complete replacing model, and it assumes that the exhaust gas is completely replaced by fresh air, and that means the gas composition discharged from the exhaust valve is totally exhaust gas. And the complete mixing model assumes that the exhaust gas is completely mixed with the fresh air. And however, the scavenge efficiency calculated by both models has error of 70% to 9% with actual result. And heavy exhaust model assumes that the gas composition discharged from the exhaust valve is mixing of exhaust gas and fresh air, so a coefficient is added to the equation. And in 1971, Valence he developed a new two-zone model. He divided the cylinder model into 2 zones, the mixed zone and the fresh air zone. And in 1991, Benson developed a scavenge model for cross scavenge. He divided cycle volume into 3 zones, and he added a short circuit zone to Valence model. The short circuit zone means that the fresh air directly discharged from the exhaust valve once entering the cylinder without mixing with the exhaust gas or pushing out residual exhaust gas. But the figure shows that the 5 scavenge model with real is not suitable for modern engine scavenge process. As we can see, all the model is not suitable for ultra long stroke engine. So our goal is to first to give a detailed discussion on the scavenge performance, and existing model are based on traditional cylinder configuration, and no scavenge model is suitable for ultra long stroke engine. We want to propose a scavenge model suitable for modern low speed long stroke well port uniform scavenge engine. We will first give an experiment method to investigate the velocity distribution at different cross section. And second, a numerical method was used to elucidate the flow mechanism of the scavenge process. And the numerical model was validated by the experiment result. And thirdly, key assumptions are refined from the flow mechanism, based on which an empirical scavenge model is built. Here we come to the experiment part. Our experiment is performed on this diesel engine, whose characteristics is listed at this table. And the entire experiment system is mainly composed of a scavenge, flow test bench, and test control system, a stereo PIV camera, blended anemometer, and other measuring system. And the original engine cylinder size was selected for the test bench measurement section to ensure that the degree of the restoration of the original engine in the test. And the scavenge pressure between the inlet and the outlet was maintained at the 3 kPa, which is the same as in the actual situation. And here are the parameters of the equipment we used. And this picture shows the average flow field obtained by assembly averaging the velocity field of 200 consecutive times. The figure shows that the change characteristic of the normal velocity cloud diagram for different axial section for the cylinder. Vortices are composed of a smaller vortex core and the annular high-speed area. The velocity magnitude at the vortex core was lower than that in the angular area. The comparison of different axial sections shows that the scavenge air flow downstream, the vortex energy began to gradually alleviate. And this picture shows that the velocity field manipulated by some well, WB is defined by this. It is the axial flow capacity of scavenge airflow in the cylinder. It is called the bulk velocity. And A is the cross-section area of the cylinder, and V is the axial velocity at different radial locations. SW is defined as is called the swirl intensity. And this picture on the right shows the scavenge non-uniformity coefficient. And now that we have measured the velocity field, but we can measure the concentration field because we don't have the equipment, and we want to do a numerical analysis to get the concentration field. This is the geometry of one single cylinder. the marine low-speed engine started here in adult well-port uniform scavenge, and a total 24 scavenge ports was evenly arranged at the bottom of the cylinder. In this study, the commercial software Converge were used to simulate the scavenge process of the engine, and the turbulence model is RNGK model. In the calculation, the basic size of the grid was 2 cm, and a 2-level dense method was adopted at the scavenge ports, and combustion chamber and exhaust valve. Safety model was mesh have been verified to be independent, as this figure shows, and the total number of mesh at the bottom dead center is approximately 1.1 million. This four pictures show the verification of the safety results. Figure A shows the cylinder pressure simulation result is in agreement with the test, and the peak heat release rate is consistent. And figure C and figure D is the velocity distribution obtained by the steady state test and those obtained by the transient simulation. To further verify the safety model, the overall degree of the scavenge non-uniformity calculated by test data and the safety was compared. And we use a safety result to develop an empirical model. And this picture shows the velocity distribution with port angle 20 degrees. And figure on the left shows the axial velocity distribution of the flow field in the cylinder at different locations. The figure shows that all axial velocity distribution is relatively systematic weak form. From the center of the cylinder to the wall, there are vortex called low speed zones and angular high speed zones and near wall low speed zones. As the air flows downstream under the action of the molecular velocity force, the velocity gradient between the layers gradually decreases, slowing a gradual decrease in the weak form ink drop. Figure on the right shows the tangential velocity distribution of the flow field in the cylinder at different locations. The traces of tangential velocity are highly consistent, thereby clearly reflect the flow characteristic of the Burgers vortex. By comparing the size of the rigid body vortex in the Burgers vortex at 1.5 and 3. As the scavenge airflow downstream, the radius of the rigid body vortex gradually becomes larger, which is consistent with the PIV test. And this picture, we use the safety to find that the scavenge process can be divided into 3 stages. In the first stage, it is called the perfect dismantling stage. At this time, the high pressure gas in the scavenge box enters the cylinder in the form of a strong jet, and a vortex structure is formed owing to the port angle, and simultaneously a part of the fresh air and exhaust gas in the cylinder are mixed at the cylinder center. This is particularly obvious as the piston descends. A large volume of fresh air rushes into the cylinder, and the high voltage quickly diffuses to the mid of the cylinder. A large percentage of combustion exhaust gas appears, indicating that the fresh air and the combustion exhaust gas are mixed violently. This is consistent with the result obtained from the scavenge non-uniformity coefficient. However, the flash charge has not reached the exhaust valve. Hence, the scavenge mode is still a perfect displacement at this time. And figure 2 shows the residual exhaust gas distribution when the piston moves towards the bottom dead center. At this time, the high vortex area is mainly located at the scavenge port and the upper mid of the cylinder. The exhaust gas in the cylinder was gradually pushed to the up mid of the cylinder. The area where the two gases are mixed is essentially the same as the high vortex area. As the piston reached the bottom dead center and began to move upward, the scavenge port is gradually closed, and the high vortex gradually spreads downstream of the flow. At this time, most of the exhaust gas in the cylinder was concentrated in the upper part of the cylinder, and the scavenge mode was mixing scavenge. And figure 3 demonstrates that when the uniform scavenge is about to end, the residual exhaust gas had been cleared. And after the flash charge entered the scavenge port, it directly flows out through the exhaust valve without encountering the exhaust exhaust gas. This process is defined as a short circuit process. To better distinguish these three sub-processes, the three-dimensional residual exhaust gas distribution obtained from the three-dimensional simulation is reduced in dimensionality. The proportion of the residual exhaust gas on each section perpendicular to the cylinder axis was averaged to obtain a y-dimensional residual exhaust gas distribution around the cylinder axis, as shown in this picture. The figure also shows that the concentration of the residual exhaust gas does not increase from the scavenge port to the exhaust valve, and the residual exhaust gas in the middle cylinder is deeply mixed with the flash charge. In addition, the proportion of the residual gas in the gas discharge from the exhaust valve positively correct with the average proportion of the residual exhaust gas in the cylinder at this time. To quantitatively describe this relationship, we define two parameters. The exhaust dense it is defined as the ratio of the residual exhaust gas portion at the exhaust valve to that in the cylinder, and the fitting exhaust dense coefficient and delivery ratio with a logarithmic function or the mix for the mixing scavenge port are as follows. The R square is 0.92, and hence the fitting is acceptable. As we mentioned, we divide the scavenge process into 3 periods. During the perfect displacement period, the gas composition discharge from the exhaust valve is total exhaust gas. So the scavenge efficiency is equal to the delivery ratio. And in the mixing scavenge period, the gas composition discharge from the exhaust valve is a mixing of the exhaust gas and fresh air. The exhaust dense is calculated by this empirical relationship with the delivery ratio. And in the short circuiting process, the gas composition does not change anymore. So we get this empirical model for the scavenge process. And next we verify this model with 4 rows they are 25%, 50%, and 49%, and 100%. And the discrepancy was maintained with 3%, and the maximum discrepancy occurs for the case with 25% load. And we also verify the model on engine performance. When the Benson model is adopted, the discrepancy in engine power is up to 5%, which is intolerable. Meanwhile, the discrepancy of BSFC and indicated power, thermal efficiency and NOx had the same bad simulation effects. In addition, the discrepancy will not be much better with the perfect mixing and perfect displacement and dense exhaust model. However, with the model development herein, the discrepancy in the engine power, BSFC, and the indicated thermal efficiency nearly disappeared, and the discrepancy of NOx stay at within an acceptable range. In conclusion, the uniform scavenge model of a low-speed engine is crucial for the calculation of low-speed diesel engine performance. However, the cylinder configuration of low-speed engine has profoundly changed the flow characteristics. Thus, the existing scavenge model cannot meet the requirement of high simulation accuracy. And we experimentally and numerically studied the characteristic of the scavenge flow in a long-stroke, ultra-long-stroke, low-speed engine, and an empirical scavenge model was developed. And we can get these 4 conclusions. The PIV test demonstrates that a strong vortex exists widely in the cylinder to stabilize the microscopic flow of the scavenge flow. And second, at the air flow to the exhaust valve, the global velocity first decrease and then increase, and the swirl intensity decrease monotonously. Furthermore, as the scavenge airflow gradually moved downstream, the scavenge non-uniformity coefficient show a clear downstream trend. And the scavenge non-uniformity coefficient is smaller when the port angle is 20 degrees. The entire scavenge process is divided into 3 sections: the perfect displacement process, a mixing process, and short circuit process. And the logarithmic relation between the exhaust dance coefficient and delivery ratio exists. And we develop a scavenge model with 3 phases, and the discrepancy in scavenge efficiency was maintained within 3%. That's all. Thank you.
Okay, thank you very much, Mr. Thompson, for this interesting presentation. Your results look quite promising. So I'm inviting any questions from the audience you may have to this presentation of Mr. Thompson. At the moment, I cannot see any questions from the audience. So please enter your questions in the questioning tool. In the meantime, while the audience write their questions, maybe I have one question to the measurement techniques. You did PIV investigations
Yes.
of the flow in the cylinder.
Yes.
Did you add any special tracer particles to the flow? And if yes, which tracer particles did you use?
if you ask, I beg your pardon.
Out of the tracer particles. So in order to do PIV, you need some particles that the camera then finds in the laser sheet. Have you added some?
Yes, yes.
What particles? Was this graphite or oil or what?
It is oil.
Oil particles. Okay. Mm-hmm.
Yes, yes.
Yeah. Thank you. In the meantime, we have a question from the audience. I can read it to you. The question is, could this model be applied in low pressure, low speed dual fuel engines to predict direct fuel slip during scavenging?
Low speed, low
pressure, low speed dual fuel engine.
I think it is unsuitable for that model.
It's possible. Okay,
yes.
so then can you predict a direct fuel slip during the scavenging process with this model?
It is only suitable for ultra long stroke, and it can be divided into 3 scavenge process.
Mm-hmm. So it is applicable also to ultra low dual fuel engines. Mm-hmm. I have here another question from the audience. The question is, do you see any limitations to applying this model to a bigger bore engine?
Big bore engine.
A bigger bore, yeah. Do you see any limitations?
No. I think if the scavenge process is I think it is suitable for it not limit. There is no limitation for big bore engines because we can also do the simulation on that engine, but the low speed engine the ultra long speed it is suitable for a large board and a large stroke and board ratio.
Okay. Thank you for these answers. Are there any other questions from someone in the audience? If not at the moment, I have a further question again to the measurement techniques. So you also presented that you measure residual gas distribution. How did you do this with PIV? Wouldn't you rather use a spectroscopic method like laser-induced fluorescence to detect species distributions? Or how did this work with PIV?
The PIV is only for a velocity measurement.
Exactly. And the species distribution? So residuals. I will just calibrate the model for the velocity profile.
Okay.
Mm-hmm. Okay.
The PIV test is only to calculate the safety result. and the model is suitable for calculating the scavenge efficiency.
Okay, okay. I see. Okay. Are there any other questions from the audience? I don't see any. So if there are no more questions to Mr. Thompson, then I would like to thank you a lot again for your presentation. And we are moving on to the next presentation in this webinar. And our second and last speaker for today is Mr. Lars Seidel from Lube Deutschland GmbH. And his presentation will be about a numerical study of NH3 diesel combustion in a retrofit for marine engines using detailed kinetics. So, Mr. Seidel, you may start. I think you're muted.
Yes. Okay. Sorry, I was somehow I was muted by an external force. Can you see a black motorbike? Is this the screen I'm sharing?
Yes, we can see it.
Great. Okay.
Looks great.
Okay. Thank you for the opportunity to present here. My name is Lars Seidel from the Lube Deutschland GmbH. We have also offices in Sweden and Poland, and if you are in the field of combustion modeling, you may have heard from us. And I'm going to present a small public-funded project here, which deals with the investigation of ammonia diesel dual fuel combustion. The project is funded by the Federal Ministry of Economic Affairs and Energy via the Projektträger Jülich, and the title is Development of Simulation Tools for Future Marine Ammonia Combustion Engines. And we are three partners, the aforementioned Lube, then the University of Rostock, the share from Professor Buchholz, and the FVTR company also from Rostock. I would like to start with the motivation why we investigate ammonia as energy carrier or fuel. Well, one big advantage is, of course, that it's a well-known production for that. So since almost 100 years, we have large-scale ammonia production via the Haber-Bosch synthesis, and the energy can be taken from renewable energies as well. We have an established distribution network for ammonia worldwide. It's the second most transported chemical in the world. It has a fairly good energy density and is comparable, easy to liquefy. So basically it is comparable to LNG. It is a very good hydrogen transport vector because it's NH3. So with every ammonia molecule, you transport 3 hydrogen molecules. And in these discussions, we have more and more that we have hydrogen alliances with other people, not Russia. We basically often mean, even though it's not publicly mentioned, that it's very likely that the carrier of hydrogen will be ammonia. And of course, if you transport ammonia, why don't you burn it in your vessel? It, of course, burns without any soot, hydrocarbon, or CO2 emissions. There's a downside. It is dangerous. If it leaks, it has a low reactivity, and meaning it has longer ignition delay times, it has a slow flame speed, and it can produce potentially more NOx and 2O emissions. Of course, if we want to use ammonia as a fuel, a good understanding of its combustion behavior is necessary, and we thought a retrofit context would be very interesting, like meaning since engines in a ship have a usually very long lifespan, it may make sense to run them partially on ammonia, replace as much as diesel as possible, and of course, on the long run, it may even be possible to replace the conventional diesel by a CO2 neutral alternative. Here is a slide from 2018, which tries to predict the use of different fuels in the future in shipping, and this predicts that by 2040 to 2050, there will be a substantial amount here, a quarter of ammonia used as fuel. This slide, of course, does not include that ammonia will be very likely in hydrogen carrier to ship hydrogen to Europe or Japan or other energy demanding countries if we are transition towards hydrogen energy. The partners in detail is the FVTR based in Rostock. That's a service provider for combustion engines, applied thermodynamics and process simulation. The Lube I'm representing here is based in Cottbus in the east of Germany, south of Berlin, close to the Polish border. And we are a software developer for fast CPU efficient tools for combustion modeling, exhaust after treatment, gas phase and surface kinetics, also coupled with other codes. And then we have the University of Rostock, the share from Professor Buchholz, so the share for piston machines and combustion engines, and they carry out the experimental investigation at this diesel ammonia single cylinder engine, which is now already running in dual fuel engine mode. The research structure, just to explain that a bit, so we have our three partners. Of course, the experiments are an important key point, and they will provide us with measurements. That's here the Lube. We develop a reaction kinetics and combustion simulation, which then we can, of course, pass back modeling results and suggestions for operating points, and we use the measurements to improve our own model. From the same measurements go to the FVTR. They provide us with thermal boundary conditions and clean post-processed engine data. We give them our fast combustion model coupled with GT power for dual fuels, which they can then use to run the whole full engine model, since we only take care of the closed cylinder. And then we have a tool for dual fuel combustion analysis. We can do some design of experiments and probably run a few more interesting points, since with dual fuels and possible different injection profiles and such things, there's a lot of variables one can investigate. So basically our development goal is the prediction of the ideal engine operating mode for dual fuel. So we go in with detailed or tabulated reaction chemistry for diesel ammonia, which means it is a reaction scheme validated against ignition delay times, flame speed, emissions, and diesel ammonia interaction. And we take the engine measurements for model development and model training, and we use our stochastic reactor model, which discretizes discretizes the cylinder or the gas phase in the cylinder into representative particles, and puts a probability density function on it, and we get out the prediction of the dual fuel combustion, and which we can then also use for combustion optimization, meaning we can shift fuel amounts, injection timings, fuel air ratios. We can try to change the mixing time and such things. I just make a very short slide on the reaction chemistry. So basically, we base the reaction chemistry on our Lube fuel reaction schemes for diesel, and we updated the ammonia chemistry from recent publications. Here, in our collaboration of Lube and the University of Cottbus, we have been very successful also in scientific publications in the field of ammonia combustion. This topic in the combustion community, so to say, in the modeling world, kicked off a few years ago, and we have been very fortunate that directly in that moment we also started with a lot of modeling and collaborations. So the diesel we model as 3-component fuel, meaning N-decane, 1-methylnaphthalene to represent the aromatic content, and methyldecanate to represent the biodiesel fraction. We have a commercial EN 590 in Europe, and the engine is fueled simply with commercial diesel. We have 2 ways to model the combustion, so we can solve the chemistry directly. That gives us CPU times in minutes per cycle, or we can solve pre-tabulated chemistry, and then we have CPU times of a few seconds to predict the combustion of the closed cycle. The general challenge here, and one reason for that project, is simply there's not much known about ammonia combustion. That was the case a few years ago. Now we have to say there's not much known about ammonia hydrocarbon interaction, and it is known from publication in the last 1.5 to 2 years that it's not a linear interpolation. So you have your very unreactive ammonia and you have a very comparable reactive diesel fuel in terms of autoignition, and you do not necessarily meet exactly in the middle. So there's a lot of things going on. In particular, you have a very important NOx chemistry with all the radicals acting on the hydrocarbons. What we can do with our diesel fuel now is we can have a 3-component surrogate, and on the right-hand side there's a small table where you see that we do not match the density perfectly, but we match the lower heating value in terms of energy per kilogram. That means if we inject the correct amount of mass measured in the experiments, we also inject nearly the correct amount of energy in the experiment, and also the CHO ratio of our surrogate is fairly close. The surrogate was, of course, so mixed that we matched the cetane number and the biodiesel content. Now, I would like to have shown experimental results. At that point, the first test bench data are available, up to 50% ammonia in mass, but they are not verified, and the experiments should have been available by today, but supply chain issues mostly and made it very difficult to set up the engine, and then I decided not to show the experiments here because they're not verified, and we simply go with some modeling results which show the idea of the tool we want to achieve, and also they are the same trends as you would see in the experiment. So we have that single cylinder engine with a bore of 110 millimeters and a stroke of 136 millimeters and a compression ratio of 16.4 to 1, which is substantially smaller than what we have seen in the previous talk. And this modeling study is performed in 3 steps. So we train our combustion model against engine measurements for pure diesel. This is here on the right-hand side, some of the experimental points, and then with an optimization algorithm, we found the correct settings for an K epsilon mixing time model. And then we have this case and setup, and we simply take this operating point and replace some of the energy in the diesel by pre-mixed ammonia. Again, in a retrofit context, it's very unlikely that you will put an additional injector in the engine somewhere. So it's much easier to inject the ammonia in the intake. And then in the third step, we change the injection timing onset to improve combustion for a fixed ammonia amount. Okay, so we have trained the combustion model for pure diesel. This is what we have available in our context, maybe from an existing engine, but of course we don't know how it would behave with ammonia. Then we now substitute diesel by ammonia, and we do that by reducing the total injected diesel mass, but we keep in this study the injection profile, shape, and the duration the same. So it's only the total amount injected goes down. And let's talk you through these slides. So in black, in all these slides here, we have the pure diesel, and then in red, we go 10% of the diesel mass is replaced by ammonia. So the amount of premixed ammonia has then the same energy content than the missing 10%. So we try to keep the total injected energy the same. And then we do that for 40 in yellow and 80 in green. And you can see, well, 80% diesel, nothing changed. 80% ammonia, it really stops burning, while the 10% doesn't do much in this context. And already 40%, we see there must be a problem. On the right-hand side, we see how the mixing time changes, and that lower injected mass simply has an impact on the mixing times. So we have a slightly slower mixing time, so to say. Okay, let's take this 40% case where we have seen, okay, 80%, that's in this setting here probably hopeless to get it to fully burn. Let's take the 40%, which burns somewhat but misses some of the combustion energy. Here, what I did in this study is I only moved the injection onset earlier. Again, we keep shape and duration the same for simplicity. Now it's a very convoluted plot, so I'm going to talk you through that as well. We start in black with only pure diesel. Then in red, 40% ammonia, so everything is 40% ammonia. That's what we have seen before. And we have the same injection timing. And then in yellow, we move the injection timing 5 crank angles earlier. Then in green 15, in where was I? Then we go to 20, which is blue, and then gray, and so on. And you can see already for this case going like 5% earlier, we reach a similar pressure trace. And here on the right-hand side, we see, okay, it's a similar pressure trace, but we do not reach the full integrated heat release. So there is definitely energy missing. And we see if we go to a much earlier injection timing of minus 20, we have, even then, we do not reach the full heat release, the full integrated heat release, which on the next slide is more apparent in the amount of ammonia in the cylinder. So they all start off with the same amount of premixed ammonia, except of the black line, which is pure diesel. And you can see, okay, no timing in no shift gives us, of course, in the highest ammonia. I would slip, so unburned ammonia leaving the exhaust. And then the earlier we inject, the more ammonia we are able to burn. All the cases end up with the same amount of CO2, so about 40% CO2 reduced because we are able to burn all the diesel. In terms of NO emissions, we can also see, first of all, the pure diesel has higher NO emissions than the cases where we see some of the ammonia burned. And this is simply because you have ammonia as reducing agent available. It doesn't burn properly. And then if the one which came closest in combustion is still below the NO formed in the diesel case, and then the more ammonia we are able to burn, the more problems we have with NO. And then there's also a case here where we see, okay, if we go back to this slide here, the -40 and -50 lines, which burn is nearly all ammonia on the right hand side there, here and here, they go to a similar level of NO model prediction as the diesel, but the clear downside here is nitrous oxide. So ammonia combustion, lean burning forms, as we see, as model prediction, but also in publications and in experiments, and substantial amount of nitrous oxide, which is a problem because it is a very potent greenhouse gas. I don't want to say that these absolute numbers here are correct, but I'm very sure that the trend itself is correct. So this is a problem which needs to be addressed, of course, either due to optimizing the combustion and try to find operating points where less nitrous oxide is formed, or by exhaust after treatment. That's, of course, if we have more measurements and we see, okay, how much are the real absolute numbers, how strong can we impact the formation of NO and N2O by changing injection profiles, injection strategy, and fuel mass. I would like to come to my conclusions. Again, I would like to have shown more experiments, but I hope that we have them soon, and we are very confident that everything is consistent, and then we will publish them. The conclusion here is that injection profiles, rate, shape, and timing are a key factor in burning premixed ammonia. Ammonia slip is an issue for larger ammonia amounts. We see that also in other publications or in other experiments. Burning small amounts of ammonia seems not to be a problem. We see a moderate rise of NO emissions, but it's probably mostly moderate because we have still ammonia present as reducing agents. We see a significant rise of N2O emissions. And the next step in our research project is, of course, more dual fuel experiments. Then based on this, looking again at the reaction chemistry and the combustion model and see if we need improvements there, what we can improve, and then tune the model against. Of course, we are going to publish this, hopefully in context of the CIMAC. And the goal is still to have a predictive combustion model for premixed ammonia ignited with diesel, in the context that, of course, you have to train the model for pure diesel measurements first. So, and I would like to thank you, and I'm very open for any questions.
Well, thank you very much, Mr. Seidel, for this very interesting presentation. We have some questions from the audience here. First question is, why don't you consider 100% NH3 engine with high compression ratio and ignition by spark plug?
This is of course possible, and there are experiments from France, now I forgot the name, where they're basically able to do that in a small SI engine, I think, very small. It is the group from Mrs. Roussel. And but that's in terms, I mean, the idea here was a retrofit context. So you have your existing engines running on diesel in ships, and is it possible to basically change them in a way that you run them at least partially on ammonia? Or if we, the argument in the beginning was a similar thing we have with LNG now, that of course the ship itself burns some of its fuel it should transport. But yes, spark plug and ammonia premixed combustion is possible. And there are experiments on that. We could model that, but this is not the focus of this project.
I see. Thank you. There are some other questions considering the lube oil. There's a question: what type of lube oil is used in the test single-cylinder engine, and is it suitable for diesel fuel or existing natural gas fuel?
I cannot answer that question. I'm not the experimental person. I assume that it is suitable for diesel because it is a single-cylinder diesel engine, and it's now modified for dual fuel mode. So I'm pretty sure that at the share from Professor Buchholz, they use the right oil.
I hope so, yes. Yeah.
So I mean, I'm sorry, that's all I can say. Of course, the follow-up question would be, do we expect any problems if we run ammonia with such a standard oil? And my answer is, I don't know.
Mm-hmm. But I think this is challenging and should be investigated, but not in this context, of course.
No, but I mean, yes, but first you need, and running, I mean, the combustion first, then the next problem. The question here is, I mean, it's basically, as the title also of the talk is basic research, we're at the point where we try to understand, and we are not the only ones, of course, how far can you go with your ammonia amount? What tools in engine operating modes do you have in an existing engine to burn as much as possible and also to mitigate ammonia slip? And even though these are just model predictions, that's of course not acceptable to waste this amount of fuel.
Okay, thanks. Then let's move on to the next questions. We have quite a couple of questions here from the audience. The next one will be, to what extent do you think the simulation can predict the experimental results?
At this point, I don't fully know, because the idea of the project is, of course, to have measurements and see what are the limitations in the chemistry with a lot of unknowns. I know that we match the ignition, so the combustion properties of ammonia and diesel very well, but the mixtures are unknown to us. In particular, even though there are a few experiments where you have rapid compression machines with pre-mixed ammonia and diesel, again, here in this context, it's different because you are first of all running very comparable lean, and then you inject, of course, one fuel into another. So here, I think we can come very close, given that we then improve our model based on measurements. But it is by far, without ever having it compared to engine experiments, not predictive at the moment.
Okay. Yeah, thank you.
Yeah.
There are further questions. One is, why is the combustion efficiency decreasing by advancing of diesel injection timing?
Why? I mean, that refers to this plot here. So what we, I think, wait, no, to this plot. Decreasing means earlier. So we go earlier and earlier. And then, yeah, this is interesting. So this is, again, just a model prediction. My understanding of what I see here is that we reach a point where we inject, I mean, and we did that. We injected also at -100. But we reach a point where we lean out due to turbulence. The diesel and diesel spray cone, so I mean, it's a spray cone which ignites, and then you go earlier. My explanation is it goes leaner and leaner and leaner, and you reach a point where you cannot even fully ignite the whole diesel portion anymore. Because again, we started with a lean engine case, and from that we took away 40% of the diesel mass. So it's the diesel part of the fuel is even leaner, and then you dilute that more and more by injecting earlier, and you may reach a point where it's even difficult to fully ignite that by compression, though again without experiments to verify that this is just a model prediction and it could be incorrect.
Yeah, understood. There is a second question from the same person. How is the effect of air-fuel ratio, compression ratio, swirl, and wall temperature in simulation and experiment? Oh,
I cannot. I mean, we do not have enough experiments to that I comment on that, and also we did not. So on swirl, well, this is somewhat replaced here in our K epsilon mixing model, so we see some impact. However, also in the experiments, we do not have models yet where we do not have experiments where the swirl ratio was changed by, how's that in English? By, yeah, putting something in the intake to have more tumble or something like that. So we are unfortunately not there yet. Also, wall temperature could be very interesting in terms of if you can get better ignition on that, but it is very clear to my understanding from old experiments that you will never reach a point where you can ignite pure ammonia by compression ignition. I think there were experiments and the outcome was something like you can do it with a compression ratio of 60:1, and well, that will never be reached in an engine. So yes, wall temperature may have an impact, but I doubt that it is an important impact. But again, that's just educated guesses here. I hope I covered all questions. Yeah, there was also the lambda, right? Yes, one could see what happens if you go to an overall richer mixture, but that's of course on the other hand then a trade-off in terms of engine efficiency. So clearly that's a completely new game here, the introduction of ammonia. While like a lot of effects in terms of combustion modeling are well understood for pure hydrocarbons and mixture of hydrocarbons, having a second non-hydrocarbon fuel in terms of combustion modeling it's a completely new world, I have to say.
yeah. Thanks for this very comprehensive answer. And the third question from the same person is about the nitrogen oxides. Did you classify thermal and fuel nitrogen oxides?
This is a very interesting question because they are, of course, now in the model. Let's answer the model, of course, predicts or includes pathways from ammonia, so the nitrogen of ammonia via the NCN, the HCN, and all the recently discussed pathways. So if you follow the publications from Krishna Shrestha from the BTU Cottbus, a PhD student from Fabian Maus, you will see there's a lot of things going on currently to understand how ammonia is formed how NOx is formed from ammonia. And of course, we have the thermal, the prompt, the Seldovich, and O. So we have a lot of pathways. I did not do any numerical investigations to see what is the dominant pathway under which conditions here. That's a bit more challenging in an engine simulation, but is a good point. One could do that in a publication later. Yeah, but the different pathways here are included in the reaction chemistry.
Okay, thanks again. So I can see no more questions. I think we already had a very intensive discussion. Well, then this was the last. Thank you again, Mr. Seidel, for your presentation.
Thank you for your time.
And this was the last presentation of today's webinar, and I would like to thank the audience for their attention and the intensive discussions, and hand the floor back to Mr. Erdmann from CIMAC. Thanks a lot.
Yes, thank you, Mr. Pirker and Mr. Seidel and Mr. Thompson for this very interesting webinar we had here today at CIMAC. It's always a pleasure to see those different perspectives, different technologies taking place, and I think we had a quite stable number of participants today. Right at the moment, it's 40 people from around the world. So I think the discussion we had shows that this topic was really relevant to the participants and really enjoyed the asking and Q&A session afterwards. I'd like to present to you the next date. So next Tuesday, again, 2 p.m., we will have the next web seminar happening right on the same channel. With CIMAC, and you will receive an invitation to this web seminar to register for it again, and you can also look on the website of cimac.com, and on our LinkedIn channel we will promote this webinar again. And next Tuesday, 2 p.m. German time, you will hear some, I think 5 presentations in total about new engine developments, diesel gas, and the new concepts and basic research. So stay tuned, look on the website, stay tuned on your email account to receive the invitation, and pleasure to meet you again next week. All the best, thank you, and have a good afternoon or a good night wherever you are. Bye-bye.